Hello everyone. So this week I will start by classifying the second order partial differential equations and reducing them to the canonical form, which has been covered in week 3 of the NPTEL videos. So I'll do some questions on that, and for theory you can always uh, go through the lecture videos that have been uploaded on the NPTEL course. So I will start. So the most general so the most general case of second order partial differential equations in two independent variables is given by a del u by del x square plus b del u by del x del y plus c del square u by del y square plus d del u by del x plus e del u by del y plus fu is equal to g, where the coefficients a, b, and c are functions of x and y, and they of course do not vanish simultaneously, because then in that case the second order PD degenerates to first order. So further, this the quotients d f are also the functions of x and y. We shall assume that the function u, x, y and the coefficients are twice differentiable in some domain. The classification of this second order PD, depends upon the form of the leading part, this part. So what we can do is, we can for simplicity write it as axy del square del u del x square plus bxy del square del u del x del y plus cxy del square del u by del y square phi of x y u del u by del x and del u by del y. Or the shorthand notations can be a u x x plus b u y u x y plus c x y u y y is equal to phi x y u u x u y. Okay. As we shall see that there are fundamentally three types of PDEs: hyperbolic, parabolic, and elliptic PDEs. From the physical point of view, these PDEs respectively represents the wave propagation, the time-dependent diffusion process, and the steady state or equilibrium processes. So, mathematically, the second order PDE is based upon the possibility of reducing this equation, uh, redu- reducing this equation called 2 by coordinate transformation to canonical or standard form at a point. The For purposes of classification, it is not necessary to restrict consideration to linear equations. It is applicable to quasi-linear second order PD as well. A quasi-linear second PD is linear in the second derivatives only. The second order PD at the second order PD, this 2 at a point x naught y naught depends on the sign of the discriminant as follows: that b2a 2c and b, which is discriminant is b square minus 4ac at the point say x naught y naught. The classification of second order PD is given by the following. If this say delta at the point x naught y naught, if this delta at the point x naught y naught is greater than 0, then the PD is called hyperbolic. If this is delta x naught y naught is equal to 0, then it is called parabolic. And if this delta x naught y naught is less than 0, then the PD is called elliptic. It should be remarked here that a given PD may be of one type at a specific point and of another type at some other point. We shall see examples of that. One of the examples is the trigonometry equation delta u del x square plus x del square del u by del y square equals to 0. You can see that b square minus 4ac will be b0, and this will be minus 4 minus 4x. So for x less than 0, that is left half plane, it is hyperbolic. For x equal to 0, it is parabolic, and x greater than 0, right half plane, it is elliptic. So a PD can be behaves certainly at one point uh, and the other way at some other point. Okay. So the okay, so one remark I would like to say that this analogy between the analogy hyperbolic, parabolic, and elliptic chosen to classify PDs reflect the analogy between the form of discriminant b square minus 4ac for PDs and the form of discriminant for b square minus 4ac, which classifies which classify conic sections, which is given by this equation ax square plus bxy plus cy square plus dx plus ey plus x equals 0. The type of curve represented by the above conic section depends upon the sign of this discriminant b square minus 4ac. If delta is greater than 0, curve is hyperbola. If delta is equal to 0, then this curve is a parabola. And again for less than 0, then this curve is an ellipse. So the analogy of the classification of PD is obvious. There is no other significant to the terminology other than and thus the terms elliptic, hyperbolic, and parabolic are simply three convenient names to classify the PDs. Now, in order to illustrate the significance of the discriminant delta and thus the classification of PD, we try to reduce the given equation 2. We try to reduce this equation 2 into a canonical form. To do this, we transform the independent variables to new independent variables epsilon and eta through the change of variables. Epsilon is equal to epsilon xy and eta is equal to eta xy, where both eta and epsilon are twice continuously differentiable, and thus the Jacobian in the region, and thus the Jacobian has to be non-zero for the transformation to be 1 1, and we can move in between the transformations. This simply means that the new independent variable can serve as new coordinate system without any ambiguity. The Jacobian non-zero means we can move between the system xy and epsilon eta without any ambiguity. So we can define Now we define W E eta to be U x E eta and Y epsilon eta. And so U x y is equal to W of eta of xy. Okay. So we apply the chain rule to calculate these following. So ux will be W epsilon epsilon x plus W eta eta x. Uy will be W epsilon eta y and plus W eta eta y. Further, uxx will be W epsilon epsilon eta x square plus 2. We are simply applying the chain rule. W with respect to eta epsilon x, eta x plus W double derivative of W with respect to x plus W eta. Okay. Similarly, you can apply a chain rule to calculate uyy and uxy, which basically we are doing this to put these values in the equation, and so that we can find a canonical form. Substituting all these values in the equation number 2, this what we'll get is a w epsilon per pw plus cw eta eta is equal to phi epsilon eta w epsilon w eta. If we become where this is a new function and the new coefficients are a, b and c, and a, b, c are expressed as you can probably write it as psi because it is a new function, is this. You can easily put this value and calculate these. Okay, and c will be now. See that at this stage this equation, we can call this 3. This equation 3 is no simpler than our original PDE, which is equation 2, but this is to be extra because so far the choices of this epsilon and eta are arbitrary. We have not imposed any particular or special conditions on that to make our original PDE to be a simpler version. So uh, what we do is, depending upon the kind of equation our original PDE is, we choose some uh, e- 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 epsilon and eta such that some of the coefficients a, b, or c, or some terms becomes zero, and and the PD becomes easier to handle, and the solution also becomes easier to find. Okay, so this brings us to our topic, which is the canonical forms. So what we'll do is which we need to construct transformations. We need to construct epsilon and eta such that which will make one or possibly two of the coefficients of the leading terms in this equation number 3 to be 0. They will vanish, thus reducing the equation to a simpler form, meaning a simpler form which is called the canonical form. For convenience, we reproduce below the original PD. If this was our original PD, and the corresponding transformed PD, where the coefficients this ABC have the small ABC have already been written above, and they of course do not vanish. And this ABC, keep in mind that they do not vanish simultaneously. Okay. Now I'll directly come to examples to let you know, and this theory has already been covered in the lectures, that how in case of hyperbolic and elliptic and parabolic, how many characteristics are there and how do we choose this epsilon and eta. So for the theory, again I'm saying, please go through the video lectures by Professor P.S. Datti to uh, know about the theory going behind it. Here I just given you a gist of what all is going on, and I'll simply move to the questions so that you understand the theory part in the lecture and you're able to solve the questions given in the assignments with the help of these live sessions. Okay, so I'll try to solve some questions. Okay, so all right, so the first question is, we'll start again as in every class. I try and start with the basics so that you can understand at least the basics very very clearly, and then we try to build up to a little difficult questions. Reduce to canonical form and find the general solution of the following second order PD: uxx plus 5uyy, sorry, uxy plus 6uyy equals 0. So the question is, we have to reduce the given PD into a simpler form and try to find the solution. Okay, so the proof or the solution, I should say. So here b is equal to 5, or I should a is equal to 1, b is equal to 5, c is equal to 6. So b square minus 4ac is 25 minus 4 into 6 into 1 is equal to 1, which is greater than 0. So this PD is classified as a hyperbolic PD. And you can, if you have gone through the video lectures of Professor, you know that this uh, this will have two characteristics. Okay, and how do we find those characteristics? Dy by dx is equal to b plus minus. Again and again I'm saying, please go through the theory part first to understand what is going on. Okay, so this will be 5 plus minus 25, which I have already 2. So dy by dx is equal to 3 and 2. which are the two characteristics. Now if we solve them, so y is 3x plus c1 and another is 2x plus c2. So what will be our new coefficients? Y minus 3x, and this will be the transformation, y minus 2x. Now see the Jacobian. If we calculate the Jacobian, epsilon x, epsilon y, eta x, eta y, which will be minus 3, 1, right? Or I would just take this to be 3x minus y and 2x minus y, just because I've already solved this using this, so be easier for me. Okay, so it will be 3, eta y will be minus 1, epsilon y minus 1, eta x will be 2, and this will be this. So minus 3 plus 2 not equal to 0. So this transformation is 1 1, and we can go back and forth between this, and hence what we can do is, so just for simplicity I'm not using u w. You can say that u is equal to u xy and eta xy. Okay, so for our equations what we need is uxx, uxy and uy. So we'll calculate all these. So what we'll get is ux will be u, sorry for my writing, u epsilon x plus u eta x. So uxx will be, in fact, what we can put the value of u epsilon x is, we know what epsilon x is, 3. Epsilon x is 3 plus u eta into eta x is 2. So this is 3u epsilon plus 2u eta. Uxx will be 3, 3, this common I can take, u eta epsilon x plus u epsilon eta into eta x plus 2 u eta epsilon x plus 2 u plus 2 already have taken 2u eta into eta x, right? So we can easily put the values of all these will vanish. This, no, it will not, because it's not eta xx. So if we put the values, we get 9 u epsilon plus 12 u epsilon eta plus 4 u eta. Okay, similarly what you can do is you can calculate uy to u epsilon minus u eta. Okay, so this uyy will be, if I take minus common, then it will be u into epsilon y plus u epsilon eta into eta y plus u eta epsilon into epsilon y plus u eta into eta y, which will come out to be, if you put the values of epsilon x, epsilon y, eta x and eta y, uh, sorry, only you have with y variable, so if we put the values of eta y and epsilon y, what you'll get is, since there is already an minus with eta y and epsilon y, so all the minus gets absorbed there, so u epsilon plus 2u epsilon eta plus u eta. Okay, Now if we now also okay, you have uxy, so you can basically you can use this, which is the value of ux with respect to y. So what you'll get is 3u psi epsilon into epsilon y plus u epsilon eta into eta y plus 2u eta epsilon into eta y plus u eta eta into eta y. So putting all the values, what you'll get is minus 3u epsilon epsilon minus 5u epsilon eta minus 2u eta eta. Okay, so now we have all the values we need to put uh, in our equation, the original equation uxx plus 5uxy plus 6uyy. So if we put all the values, what we'll get is we get u epsilon eta is equal to 0, which is a canonical form. Also you can see that in the canonical form b is equal to 1, a is equal to 0 is equal to c. Again the canonical form implies the canonical form obtained is hyperbolic, meaning that it has retained the classification of the original PDE we had, and it has turned out to be the same. Canonical form attained is same, has the same classification, you can say. As the original PDE. So now also we can, now it is very easy to find the solution. What the solution will look like, u epsilon eta is equal to 0, so we integrate with respect to eta to get u epsilon is equal to some function of f eta, right? We have integrated with respect f epsilon. Okay, now again integrating with respect to epsilon, we get u is equal to some another function of f epsilon plus some function of g eta, and now we know that epsilon is equal to 3x minus y and eta is equal to 2x minus y, implies u is equal to f 3x minus y plus g 2x minus y is the general solution. Okay, so this is how the solution will look like. Okay, so I think with this example it is very clear on how to reduce the given PD into canonical form, which is easier to uh, understand. Okay, so I will do some more questions for you guys to have a very clear picture and help you solve more and more questions. Okay, so question number 2 is, reduce to canonical form and find the general solution. Week 6, this is the equation 2yuxy plus uyy is equal to ux plus 6y. Okay, so again the question is to we have to reduce it to the canonical form and find the general solution. So so here at a is y square, b is minus 2y, c equals to 1. B square minus 4ac is 2y square minus 4y square into 1, which is 0. So implies parabolic PDE and implies one characteristic. Again, for that you have to see one characteristic because the discriminant will be 0 and it will get two repeated roots, basically one root. So our again we'll find characteristics as b plus minus b square minus 4ac by 2a. So dy by dx is equal to minus b square minus 4ac by 2a. So b square minus 4ac is 0. So this will be minus 2y by 2y square. Okay, so what we have is so dy by y is equal to minus x dx. We get y square by 2 is equal to x plus c1. So we can choose our eta to be x plus y square by 2. Now from here we have only gotten one characteristic. So for the second and hence one function eta xy, and for the second function what we'll do is we'll to choose eta such that the Jacobian matrix is non-zero. So we'll choose eta to be y. So if you calculate now the Jacobian, which will be eta x, sorry, epsilon x, epsilon y, and eta x, eta y, which will be 1, and this will be y. Eta x will be 0 and 1 is equal to 1, which is non-zero. So we can choose this eta. This is the Jacobian is non-zero, and then we'll work with this two functions. Epsilon is equal to y square by 2 plus x, and eta is equal to y. Okay, so now we have these two functions. What we'll do is we'll again calculate all the things we need to put in our original equation, this equation, and again we need all these things which are uxx, uyy, uxy, and ux. Okay, I'm sorry, I think there's again a problem with my network. Just give me a few minutes. try to figure this out. Hello, I'm sorry for the disruption, but I think my network is stable now. I'll try to write once and see if. Yes, it is visible now. Okay. So where were we? So this was a question. We have found the two characteristics of our function, the transformation epsilon and eta. Now we'll calculate our required things. So there's one 0. This is very frequently used, so it is better to write it down neatly. It's equal to 1. Okay. So now u is equal to u function of psi, which is further function of x and y. Okay. Now ux will be u epsilon x plus u eta into eta y. Now we have all these values here, and we can put this to get this to be u epsilon. So u x will be u epsilon x plus u epsilon eta x. Now again, eta x is 0, so this and epsilon x is 1. This is u epsilon. Now uy will be u epsilon y plus u eta y. Is there anything which is to be 0? No. Okay, so this will be y into u epsilon plus 1 into u eta. Now uyy will be so here we'll have to put we'll use the product rule. So u epsilon plus y into u epsilon eta into eta y plus u epsilon into epsilon y plus u eta epsilon into epsilon y plus u eta into eta y, right? So this will putting all the value will get u epsilon plus y square u epsilon plus 2y u epsilon eta plus u eta eta. Okay, so what we are left with is uxy. So this will be u epsilon differential epsilon with respect to y, which will be u epsilon into y plus u epsilon eta into eta y, which is y into u epsilon eta y is y, eta y is 1 plus u epsilon eta. Putting again, we'll put all these values. We'll put all these values in the original equation, all these uxx, uxy and uyy. So our canonical form will be sorry. So our canonical form comes out to be u eta is equal to 6y. Also, we have to find the canonical forms in terms of the new variable. So again, we'll put the value of y, which was nothing but eta. So our canonical form is u eta is equal to 6 eta, right? Now we have to find general solution. Again, we'll integrate with respect to eta twice to get u eta is equal to 6 eta square by 2 plus some function of epsilon, because u is a function of eta and epsilon. So again, integrating it with respect to eta to get, so u eta is 3n square plus f epsilon. So again, integrating with respect to integrating eta twice, we get, again we'll get 3n cube by 3 plus eta into f epsilon plus some function of epsilon. Now our eta is y and x plus y square by 2. So our general solution becomes y cube by 3 plus n f epsilon is x plus y square by 2 plus g x plus y square by 2. So these are our general solution. Hence, we have found what the question said to find the canonical form and to find its general solution after reducing it to the canonical form. So you can see that after reducing it to the canonical form, the solution becomes very easy to find, because the canonical forms itself becomes so easy, so that it is very easy to differentiate and integrate, to play around with that. So that is the main idea behind the canonical form. So to reduce our complicated second order PDEs into such a form by applying such some transformations such that it reduces into a simpler version, so that we can easily find its solution. Alright, so and you'll see that we choose our epsilon and etas very smartly, so that some of the coefficients become 0. And again you can see that this equation is again, what was our original equation? Parabolic. So here b is equal to 0 and our a is equal to 0. Again a parabolic, and try to figure out a c, y, and how this happens, that the classification of PD after reducing it, after applying a transformation, is still the same. What is the logic or theory behind it? This is an interesting exercise. Okay, so next is, so we have covered two questions, one concerning the hyperbolic PD and the other one. First one was a hyperbolic PD, and the second one was elliptic, sorry, parabolic, which had one characteristic, and the other one was uh, hyperbolic, which had two characteristics, which gave us the transformation. And here we had only one characteristic, which gave us that transformation by choosing the other one such that the Jacobian is non-zero, and that worked well for us. Okay, so next question is, we'll try to do one question on the elliptic type of PD. Question 3 is, show that the equation is elliptic everywhere except on the coordinate axis. X is equal to 0. Find the characteristic variables and reduce to, basically you can simply say that, reduce to canonical form. Okay, so the question says that we have to show that this is elliptic everywhere except on the coordinate axis, like x is equal to 0, and we have to further reduce the equation to the canonical form. So the solution is, so here a is 1, b is 0, c is equal to x squared, so b square minus 4ac is equal to minus 4x squared, which is less than 0 for except, sorry, except for x equals to 0. Okay, therefore implies the PD is elliptic except on the coordinate axis x equals 0. Okay, so now we'll find the roots by basically, so our lambda 1 will be b minus epsilon. We have iota, we are already putting iota outside, 4ac minus b square by 2a, which is b0 minus iota into 4x square, which will be 2x by 2. So minus iota x, and the second root will be lambda 2 is equal to b plus iota 4ac minus b squared by 2a. So plus iota into 2x by 2, which is iota x. So the characteristic equations are dy by dx is equal to minus iota x, and I should probably write it down neatly. Place the characteristic equations are dy by dx is equal to iota x and dy by dx equals iota x. So if we try and solve these, what we'll get? Y is equal to minus iota x squared by 2 plus c1, and y is equal to iota x squared by 2 plus c2. So see that there are no real characteristic curves here. So we see that the two families of complex characteristics are of complex are given by y plus iota x squared by 2 is equal to constant, and y minus iota x squared by 2 is equal to constant. So how do we do the transformation here? So transformation, what we do in this case is alpha, if we, these are the two families, now real and imaginary parts of alpha and beta gives us the required transformation. Variables eta and epsilon and eta. So thus we have, what we do is, for mathematically if you want to write, epsilon is alpha plus beta by 2, which is y, and eta is alpha minus beta by 2i, which is x squared by 2. So with this choice of coordinates, we'll try to reduce our equation to the canonical form. So we have eta is equal to y and epsilon is equal to y and eta is equal to x squared by 2. If we get Jacobian, epsilon x is 0, epsilon y is 1, eta x is x, and the eta epsilon is 0. Not equal to 0 as we have considered x to be non-zero. Okay, so now we'll apply our transformation and we'll see that ux is u epsilon eta x square plus u 2u epsilon eta into epsilon eta x plus u eta into eta x square plus u eta into eta xx plus u eta into eta xx. Okay, so this will be x square u eta plus u eta, and uyy is u epsilon into epsilon y square to u epsilon eta into epsilon y eta y plus u eta into eta y square plus u epsilon y plus u eta into eta y, which is u epsilon epsilon. So substituting the original equation, we get u epsilon epsilon plus u eta eta is equal to minus 1 by 2 eta u eta. Now also we have taken eta to be x square by 2, implies x square is equal to 2 eta. So implies our equation becomes u epsilon epsilon plus u eta eta minus 1 by x square u eta. So finally the canonical form is u eta eta plus u epsilon epsilon plus u eta eta. Oh, I'm really so, we already had it in terms of theta, so we don't need to do anything here. Actually, when we calculated, what we had is we use this fact that original equation, and using the fact that x square is equal to 2 eta, we get the following canonical form. Okay. Okay, so we have our we have reduced the equation to the canonical form, and this was what was asked in the question. Now see that we have done 3 questions on hyperbolic, parabolic, and elliptic. Alright, so I'll do a couple of questions more for a better understanding. So see the next question. Find the characteristics of the following partial differential equation, which is x u x x plus x minus y u x y minus y u y y and transform it to a canonical form and use that canonical form to find the general solution. So we have to find the characteristic, reduce it to the canonical form and find its general solution. So the solution is, so see that so here what we have is a is equal to x, b is equal to x minus y, c is equal to minus y. P square minus 4ac is okay, and see that we have been given x and y to be greater than 0. So this is implies hyperbolic PD implies 2 characteristics. So we don't have to worry about finding the characteristics. We already have a natural naturally two characteristics, and hence are two variables, two new variables, epsilon and eta. So dy by dx which is x minus y plus minus, which is 4xy by 2x, which comes out to be 2x by 2x is equal to 1, and minus 2y by 2x is equal to minus y by x. So our characteristic PD we can say is implies y is equal to x plus c1, and dy by dx is equal to minus y by x, which is dy by y is equal to minus dx by x, and integrating what we get, log y is equal to minus log x plus log c equal to c by x. Y implies yx is equal to c2. I can say this c2. So what we take is our epsilon to be say x minus y and eta to be xy. If you calculate the Jacobian, epsilon x is 1, epsilon y is minus 1, eta x is 1, eta x is y, and this is x, so is equal to x plus y not equal to 0 for x greater than 0 and y greater than 0. Alright, so we have a 1-1 transformation. Now you can see that we have to calculate all these values to put it in the equation, so I'll write it down as I have already calculated these to get. So u is equal to u epsilon eta xy, epsilon xy and eta xy. So ux is u epsilon plus y u eta, and uy is, you can calculate this. Okay. So uy will be u epsilon plus x u eta, and uxx will be u epsilon into u plus 2y u epsilon eta plus y square u eta eta. Uyy is equal to u epsilon minus 2x u epsilon eta plus x square u eta eta. Now what we get is x square plus 2xy plus y square u epsilon eta plus x minus y u epsilon eta u eta is equal to 0. So that is x minus y square plus 4xy u epsilon eta plus x minus y u eta is equal to 0, which is epsilon square plus 4 eta u epsilon eta plus epsilon u eta is equal to 0. Okay, which is the canonical form. Now we have to find the general solution. The general solution is, what we can do is, we'll use a trick here. So we have We just have to manipulate the canonical form we got in. So, what we have is u epsilon eta is equal to minus epsilon u eta upon epsilon square plus 4 eta, right? So what you can do is u epsilon eta or what you can write it like u epsilon u eta with respect to the epsilon, and u eta is equal to plus 4 eta. Integrating eta, we get u eta epsilon upon u epsilon d eta is equal to minus 4 eta, right? It is integrated with respect to epsilon because we have this here. Okay, what we have is log of u epsilon equals to minus 1 by 2 if this is the derivative above of log epsilon square plus 4 eta plus some function of eta, right? So this will simplify it a little further to get so what you get is some, you can write it as log fn to get you can write it like log, you know what it is. Okay, place. So again if we integrate with some function of epsilon plus to the minus plus some data, right? This is a general solution. Okay, so by now I hope you can classify the PD, then solve it, then find the characteristic curves, and then find the new transformation so that it is 1 1, and then you reduce it to the canonical form and use that canonical form to find the general solution. So I hope by now you can do all these things very easily, right? Okay, so I hope this will be very helpful in your solving the assignment questions. All right, I'll do one more questions again for a better understanding. Consider the minus x u y is equal to 0. So this is a second order PD of mixed elliptic and hyperbolic type. So again we have to reduce it to the canonical form. Right, this is a second order PD of mixed elliptic and hyperbolic type. I'm sorry I was not able to, I think, share the screen of a Miss OneNote. I think you can see it now. So I'll continue with the question. So will be 4x. You can check this. So this will be hyperbolic for x greater than 0. It will be hyperbolic and x less than 0. It will be and equal to 0 parabolic. We are assuming assume x greater than 0, so we'll have two characteristics again, b plus minus b square minus 4ac by 2a will be plus minus root x. So we have considered x greater than 0, so this makes sense. So two characteristics are dy by dx is equal to root x and dy by dx is equal to minus root x. So our y is 2 by 3, x is 3 by 2 plus c1, and y is equal to minus 2 by 3, x 3 by 2 plus c2. These are the two constants, and we have two family of characteristics curves, and so we take epsilon equals to y minus 2 by 3, x 3 by 2, and eta is equal to y, right? So we have again calculate the Jacobian and check. It comes out to be non-zero. So calculate these things. Epsilon y is equal to 1, epsilon x is equal to minus 1 by 2 root x, epsilon y is equal to 0, eta x is equal to root x, eta y is equal to 1, eta xx is equal to 1 by 2 root x, and eta y is equal to 0. So uxx will be w epsilon x square plus w epsilon x eta x plus w eta and eta x square plus w eta into eta xx plus w eta into eta xx, which comes out to be xw epsilon minus 2xw epsilon eta plus xw eta minus 2 minus 1 by 2 root x w epsilon plus 1 by 2 root x w eta. So nuy is equal to w epsilon eta y squared plus 2w epsilon eta y epsilon y eta y plus w eta 2 eta y squared plus w epsilon y plus w eta. This is not w. In our case, we have chosen it to be u only. So this is u, 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 u eta plus u epsilon y plus u eta into eta y equal to u epsilon plus 2u plus u eta. Also, we have x3 by 2 is equal to 3 eta minus epsilon by 4. Substituting in the given PDE, we get u epsilon eta is equal to 1 by 6 u epsilon minus u eta by epsilon minus eta. This is the required canonical form of the trigonometry equation in case of the hyperbolic region. Similarly do for parabolic and elliptic region. Okay, so I hope I'm clear on these canonical forms, how to calculate them, and I hope you'll be able to solve the assignment questions. We'll meet I will wait for you guys to if you have any questions, and I am here if you have any query or doubts. And I'll meet you next week with the next topic and your questions. Thank you.